Hello everyone, my name is Renji Z. Villorente, BSc E4A, and my topic is about position vector, velocity, and acceleration. So in most practical applications, we are interested in the position or the velocity or speed of the particle as a function of time. Therefore, we need equations that relate the position, velocity, and acceleration. So first, let's define position vector. Position vector is defined as a fixed vector that locates a point in space relative to another point. So now we will specify the position of a particle using the Cartesian components of its position vector with respect to a convenient origin. So this means we choose three perpendicular fixed directions in space. So these three directions are described as unit vectors, is I, J, and K. Then we choose a convenient point to use as origin. And then the position vector relative to the origin is specified by the three distances x, y, and z in the figure. So in this manner, we can define the position vector from the origin to the point and represent as r for the equation. So next is velocity. By definition, velocity is the derivative of the position vector with respect to time. Velocity is a vector, therefore can be expressed in terms of its Cartesian components. V is equals to Vxi plus Vyj plus Vzk. We can visualize a velocity vector as follows. The direction of the vector is parallel to the direction of motion. The magnitude of the vector is the speed of the particle, for example, in meters per second. So the magnitude of this kind of velocity vector can be simply found by the magnitude of the vectors is equal to the square of bx squared plus by squared plus vz squared. So now when both positions and velocity vectors are expressed in terms of the Cartesian components, it is simple to calculate the velocity from the position vector. So for this case, the basis vectors I, j, and k are constant, and so v sub xi plus b sub yj plus v sub zk is equals to the derivative of x times ti plus y times tj plus z times tk. Then is equals to the derivative of x with respect to time I plus the derivative of y with respect to time j plus the derivative of z with respect to time k. And so the equation for each velocity components to be v sub x is equals to dx dt and by is equals to dy dt, then vz is equals to dz dt. So last, acceleration. By definition, it is the derivative of velocity vector with respect to time, or equivalently, it is the second derivative of position vector with respect to time. So acceleration is a vector, therefore can be expressed in terms of its Cartesian components. A is equals to a sub xi plus a sub yj plus a sub zk. Like velocity, acceleration has magnitude and direction. Sometimes it may be possible to visualize an acceleration vector. For example, if you know your particle is moving in a straight line, the acceleration vector must be parallel to the direction of motion, or if the particle moves around the circle at a constant speed, its acceleration is towards the center of the circle. But sometimes you can trust your intuition regarding the magnitude and direction of acceleration, and it can be best to simply work through math. So the acceleration is a a sub x is equals to dvx over dt is equals to d square x over dt square, and a sub y is equal to dvy over dt is equals to d square y over dt square. Az is equals to dv z over dt is equals to d squared z over dt square. So these are some examples. First is a particle has a velocity of 5.0 t I plus 2 squared j minus 2.0 t cubed k meter per second. A. What is the acceleration function? B. What is the acceleration vector at t is equal to 2.0 seconds? Find its magnitude and direction. So first, we take the first derivative with respect to time of the velocity function to find the acceleration. By differentiating the given, we get 5.0 I plus 2.tj minus 6.0 t cubed k meter per second squared. And then by substituting t to 2.0 seconds, we get 5.0 I plus 4.0 j minus 24. K meter per second squared. So the answer gives us the direction in unit vector notation. So the magnitude of the acceleration is equals to the square root of 5.0 square plus 4.0 square plus minus 24 squared. And the answer is 24.8 meter per second squared. Here the second example. So a particle has a function of 10t minus t squared times I plus 5tj plus 5tk meter. What is the velocity? B. What is the acceleration? So by looking at the position function of the problem, it is linear in y and z. So we know the acceleration in this direction is 0. When we take the second derivative, also note that the position in the x direction is 0 for t is equals to 0 seconds and t is equals to 10 seconds. So by taking the derivative with respect to time of the position function, we find 10 minus 2t times I plus 5j plus 5k meter per seconds. So the velocity function is linear in time in the x direction and is constant in the y and z direction. By taking the derivative of the function, we find the acceleration with respect to the function of time is equals to the negative 2I meter per second squared. The acceleration vector is constant in negative x direction. So the answer is thank you.